There is often more than one way to solve a mathematical problem, and sometimes one way is easier than the others. Usually the easier one has been discovered after people spent many hours and even years calculating the slower way. Hi, my name is Jason Rosenberry, and today we will be exploring linearization, sensitivity, differentials, and also Newton's method. Let's start with a definition. Definition: linearization. If f is differentiable at x equals a, then the equation of the tangent line, L of x equals f of a plus f prime of a times the quantity x minus a, defines the linearization of f at a. The approximation, f of x is approximately equal to L of x, is the standard linear approximation of f at a. The point x equals a is the center of the approximation. Let's try an example. Let's let f of x equal x plus 1 over x, and let's let a equal 1. Part A, find the linearization L of x of f of x at x equals a. And part B, how accurate is the approximation L of a plus 0.1 equals f of a plus 0.1. So again, we have f of x equals x plus 1 over x, and a is equal to 1. To find the linearization, we will need the derivative of f. So let's find f prime of x. F prime of x would equal 1 minus 1 over x squared. The linearization equation is L of x equals f of a plus f prime of a times x minus a. So we will need to find f of a and also f prime of a where a is equal to 1. So let's find f of 1. F of 1 would be 1 plus 1 over 1, so that's 2. Let's also find f prime of 1. So evaluating the derivative at 1 gives us 1 minus 1 over 1 squared. 1 minus 1 is 0. Now we can find our linearization equation. L of x is equal to f of a, where a is 1, so f of 1 is 2, plus f prime of a, in this case again a is 1, it's a 0, times x minus a, again a is 1. Simplify, we get L of x is equal to 2. Part B to our problem wants us to compare L of a plus 0.1 versus f of a plus 0.1. So using a equals 1, we will substitute that into each one. So we would get L of 1.1, and we want to compare that with f of 1.1. L of 1.1, function L tells us that it's a constant function, so we always get 2. So L of 1.1 is 2. So that's our approximation. The actual function value at 1.1, substituting 1.1 in for f of 1.1 is 2.009. And as you can see, our approximation is very, very, very close. It only differs by less than 1/100th. Now let's look at differentials and sensitivity. Definition: differentials. Let y equals f of x be a differentiable function. The differential dx is an independent variable. The differential dy is equal to f prime of x dx. Sensitivity. Sensitivity is an interpretation of the derivative, describing how small changes in the input variable produce changes in the output variable. For small values of delta x, meaning small changes in the input variable, we can approximate delta y. Delta y means this change in the output variable. We can approximate that change by delta y equals dy dx delta x. Let's try an example. Given that y equals x squared times the natural log of x, and x equals 1, and dx equals 0.01, part A, find dy. Part B, evaluate dy for the given value of x and dx. Let's begin by finding the derivative of y. We're treating y as f of x, so f prime of x using the product rule would be first times derivative of the second plus second times the derivative of the first, which is 2x. Simplifying, we get f prime of x equaling x plus 2x natural log x. So to find dy, we need to take f prime of x times dx. In this case, x is 1. So dy would equal f prime of 1. F prime of 1 would be 1 plus 2 times the natural log of 1. And then we're going to multiply all of that times dx, and we're told that dx is 0.01. And when you compute that, dy is equal to positive 0.1. So what's this telling us? This is telling us that a small increase in x, a small increase of 0.01, will result in a small increase of y of about 0.01. We often use differentials to estimate change. There are 3 types we can find. Let's take a look at them. We have absolute, relative, and percentage change. Absolute change, the true value, the true change in f of x, is equal to f of a plus delta x minus f of a. The estimated absolute change, df, equals f prime of a dx. Relative and percent change. Here we have the true changes, delta f of x over fa, and to simply change that to a percent, we're multiplying by 100. Over on the estimated side, the estimated relative change is df over f of a, and again, to change that to a percent, we're just multiplying by 100. In the late 1830s, the French physiologist Jean Puiseux discovered the formula we use today to predict how much the radius of a partially clogged artery has to be expanded to restore normal flow. His formula, V equals kr to the 4th power, says that the volume V of fluid flowing through a small pipe or tube in a unit of time at a fixed pressure is a constant times the 4th power of the tube's radius r. How will a 10% increase in r affect V? So let's start with our formula, V equals kr to the 4th. And let's go ahead and differentiate both sides of this equation with respect to r. So we would have dv dr is equal to 4k r cubed. And now let's multiply both sides of this equation by the differential dr. So that gives us dv is equal to 4k r cubed dr. Let's now evaluate dv over v. This would be the relative change in v. So this would equal numerator dv, which is this expression, 4k r cubed dr, over v, which was given to us as the formula. So v is equal to k r to the 4th. Let's simplify this fraction. So dv over v, the relative change in volume, equals, we would have a 4 in the numerator, the k's divide out, r cubed divided by r to the 4th leaves us with an r in the denominator, and we have a dr in the numerator. So we have 4 dr over r, and that can be rewritten as 4 times dr over r. So the relative change in V is equal to 4 times the relative change in R. Therefore, a 10% change in R meaning if dr over r is 10%, then 4 times that would be 40%. So a 10% change in r will produce a 40% increase in the flow. A manufacturer contracts to mint coins for the federal government. The coins must weigh within 0.1% of their ideal weight, so the volume must be within 0.1% of the ideal volume. Assuming the thickness of the coins does not change, what is the percentage change in the volume of the coin that would result from a 0.1% increase in the radius? Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So starting with our formula V equals pi r squared h, let's differentiate both sides of the equation with respect to r. So on the left, that gives us dv dr, and over on the right hand side, the derivative of that expression with respect to r, we will treat h as a constant. So that gives us 2 pi r h. Now multiplying both sides by the differential dr, we get dv is equal to 2 pi rh dr. Now let's evaluate the expression dv over v. dv is this expression, 2 pi rh dr over v, which is our formula. So v equals pi r squared h. Now we will simplify. So dv over v equals, we have a factor of 2, pi's divide out, we're left with a factor of r in the denominator, the h's divide out, and we have dr in the numerator. We can rewrite this as dv over v is equal to 2 times dr over r. So the relative change in v is 2 times the relative change in r, so a 0.1% change in r will produce a 0.2% increase in v. Now let's take a look at Newton's method. Procedure for Newton's method. Guess a first approximation to a solution of the equation f of x equals 0. A graph of y equals f of x may help. 2. Use the first approximation to get a second, and then the second to get a third, and so on, using the formula x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. Let's try an example. Use Newton's method to estimate all real solutions of the equation. Make your answers accurate to 6 decimal places. The equation is x cubed plus x minus 1 equals 0. Newton's method requires the first derivative. So if we let f of x be the left-hand side of the equation, x cubed plus x minus 1, then f prime of x, the first derivative, would be 3x squared plus 1. Now we can substitute these values and functions into Newton's method. X sub n plus 1 equals x sub n minus f of x sub n over f prime x sub n. So we would have the expression x sub n plus 1, which represents the next approximation, or the second, or the third, or the fourth, equals x sub n minus f of x sub n. So function f is x cubed plus x minus 1. So we would have x sub n cubed plus x sub n minus 1 over f prime of x sub n. So that would be 3 times x sub n squared plus 1. So to get this process rolling, you need a first approximation. You need a very first value to begin this approximation process. So as you recall in a previous slide, you want to try to guess a value that causes the function to equal 0. So if we were to look at the graph of x cubed plus x minus 1, we see that a very good approximation for a value of x that would cause the function to equal 0 is 0.68232278. So you would take that value, and that would act as your initial guess. So x sub 0 would equal that 0.6823, etc., etc. So let x sub 0 be that. Then x sub 1 would equal x sub 0 minus the expression over here evaluated at that decimal. So that would give you x sub 1 that you reuse again to find x sub 2, that you reuse again to find x sub 3, and you keep going until you get the desired level of precision. There is a method that you could use your graphing calculator to mimic Newton's formula, Newton's law. Let's try that again, Newton's method. So let me show you the graphing calculator way of this process. Start with the graph again and choose that value that's a good approximation for f of x equaling 0. So in this case that would be 0.6823278. Then on your graphing calculator, enter the function, meaning enter f of x in y1 and enter the derivative f prime of x in y2. On the home screen, store the initial guess into x. That would be our 0.68232278, etc. Then type x minus y1 divided by y2, store that as x. So again, this is a recursive definition. And keep pressing the enter key over and over. Watch as the numbers converge to the 0 of f. When the values stop changing, it means that your calculator has found the 0 to the extent of its displayed digits. So just showing you this, we stored our initial guess, 0.68, in for x. Type in the formula x. This is after you've entered the function in for y1 and its derivative in for y2. Then type in x minus y1 over y2, store that as the new x, and then keep pressing the enter key. And then you can notice that out here is where our precision is starting to get closer and closer and closer to that true 0. So these two are the same, other than maybe some differences way out here. So this would be a very, very good approximation of the value of x that causes f of x to equal 0. In this lesson we explored linearization and Newton's method. Be sure to work the exercises that your teacher assigns, and we'll see you next time.